Hello and welcome, one and all, to the Quimper Geological Society event. My name is Rebecca Koronowski, and I will be one of your hosts for the evening. I want to start off right off the top here with a couple of tech orientation pointers. So first off, in the bottom of your screen, you may be seeing some closed captioning. We have that available in case folks need it, but if you do not need it, I would like to give you a little info on how to turn that off. So in the bottom, roughly center of your screen, there's an icon. It's a square that has it says CC on it. And if you click on that, it gives you the option, if you click the up arrow, it gives you the option to hide the subtitles. So you may see either show subtitle or hide subtitle, and that'll allow you to choose if you'd like to see those captions there. Additionally, we're going to have the audience on mics muted for the duration of the event, just so we can prioritize our speakers' voices. However, I do encourage you to turn on your camera if you'd like, just to give us a sense of who's in the audience and gives Doug someone to pay attention to and watch your reactions as he's going along. We will be recording this presentation and sharing that with you at a later date. However, we will not be recording your video feed, so don't worry about that. We'll just be sharing the slides and the speakers. Throughout the session, feel free to send messages into the chat. And for those of you who may not know, in the bottom of your screen, if you're on a computer, there's a little speech bubble. I just typed in hi, so you could see that pop up. And you can send your questions to everyone in the chat so we can all see which questions are coming in. If you're on a phone or a tablet, you may have to choose the 3 dots more button in order to find the chat option in the menu there to send chats to us. And feel free to send those throughout the session, and Michael and I will be compiling them and asking them of Doug at the end of the session. We'll plan to end the formal part of the presentation at about 5, at which point we'll then turn it over for the Q&A. And so right off the top here, I'd like to get a sense of who we have in the audience. If you've been to any of these sessions before, this may be familiar for you. If it's not, on your screen, you'll have 2 questions that should have just popped up. One to answer where you're from, and one to answer what your geologic background is. And you can either click or tap, depending on your device, on your answers, and then click submit. And the results are coming in, and once we get a good number of them, I'll share with you so you can see who we have in our audience with us tonight. It's always fun to know. Yeah, and I guess I will answer that I'm in Port Townsend and I have undergraduate study in geology. I'm curious what some of the others are in the geologic background field. We have a couple of folks who are saying something other, some other experience with geology. So I'll give just a couple more seconds here, and if you end up missing it and I end the poll before you submit, feel free to add those to the chat as well. Okay, here we are. So folks, mostly outside of, in Washington, but outside of Jefferson County at 39%. And then Port Townsend folks, and a little bit within the county as well. Thanks for being here. No international folks with us tonight. Sometimes we have people tuning in from different countries. And then geologic background, a lot of folks who are new to geology or might not necessarily have formal study in geology. So that's great, and that'll help us to shape some of our additional commentary. So thank you all for being here. And I am now going to turn it on over to Michael Machette, leader of the pack here. Come on, Michael. Let's get your mic unmuted. There we go. Hi, Michael. How you doing tonight?
Hi, you guys, everybody. I changed my screen here. Oh, I see Rebecca. Anyway, thanks for coming today. It's kind of a dreary day in Port Townsend, but hopefully it'll be clearing up and getting warmer. We have some upcoming events. The next two things in 2022 talks on January 8th, right after New Year's. Carolyn Dreiger, I don't think I pronounced her name right, is going to give a talk that compares the volcanic hazards from the Nevado de Ruiz volcano in Colombia, which erupted massively about 20 years ago, and that of Mount Rainier here in Washington. They have very much similarities and lessons we can learn from Colombia here in Washington. Then on February 19th, Marley Miller, who's an expert photographer and well-traveled throughout the western U.S., is going to go through some of the points in her Roadside Geology of Washington, which is a book she wrote with Terrell Highlands about 5 years ago. So if you're ever taking a road trip, put this in your glove box and you've got about every outcrop in Washington detailed. So as Rebecca said, we're recording these events. We have about a dozen recorded events. We're in the process of porting them over to a new server, and hopefully in the next week or so, all the recorded events will be available through our website. So I want to introduce Doug now. There she goes. So our speaker today is Doug or Douglas Clark. He's an associate professor of geology at the Western Washington University in Bellingham. He received bachelor's and master's degrees in geology at Stanford University, went on to get his PhD in geologic sciences from the University of UW right here in Seattle. He's also worked as a geotechnical geologist for Earth Science Associates in the Bay Area between his advanced degrees. Doug's research interests span a broad range of Earth science phenomena related to mountain landscapes, including glaciation and climate change, landslides, and active tectonics. His research has taken him to Central Asia, Australia, New Zealand, and most of Western North America. But he maintains a special interest in the glacial problems of the North Cascades, including Mount Baker, which we'll focus on today. Interestingly, I want to mention that I have not met Doug in person. We've had video chats here several times, Doug. But thanks to COVID, we're sort of restricted. But I did work with his father, so Doug is a second-generation geologist. Back in the early 1980s, and I remember his dad, Malcolm, and my times together chasing the 1979 Bora Peak earthquake in Idaho. By my calculations, Doug was a freshman at Stanford at that time. Does that sound about right?
Probably about right, yeah.
Okay, close enough. Interestingly, today is Doug's six-year-old daughter's birthday. Her party's ongoing right now, so let's all wish her a happy birthday. And hopefully her dad can join in the chaotic end of her party. Okay. So without any further ado, I'd like to introduce Doug Clark. His talk is entitled Under Ice and Water, New Constraints on the Final Advance of the Cordilleran Ice Sheet in Northwestern Washington. Doug, it's all yours.
Well, thanks, Michael, and Rebecca. I want to thank you guys both for inviting me here, and to the rest of you all for attending. I think I've got to say this is probably the biggest Zoom presentation I've done yet. So you guys hit the top mark on that one. So I'm gonna go ahead and share screen here. I also want to say I also recognize a few folks out there, like Ralph does, and I saw Ralph Haggerty. I have two Ralphs that I've known for quite a while are in the audience too. So, and I know Ralph Haggerty, you've given a presentation, I think, to Quimper Society too. So anyway, hopefully I can sort of do justice to your guys' presence here as well as everyone else. So let me share screen here, and we'll get going. I'm going to move my camera over so I'm looking at you guys when I'm talking. So as Michael mentioned, we've got this title this is a study I've been working on for quite a while on some constraints on this last gas readvance of the Cordilleran ice sheet right up in our backyard here in Bellingham and Whatcom County. And it's got some unique aspects of it in terms of this readvance spanned the border, the international boundary, which wasn't there, of course, at that point, but it is there now, and that has led to some of the disagreements about what's going on with this advance. It's sort of a confusing time period in many ways, and so there's some heated debates about what happened up in our neck of the woods during this last gas glacier advance up here. So we'll talk about that today, and it's got a lot of moving parts in it, and I'm going to try and keep it as simple as possible, but not to make it all fairly comprehensible to people who are just seeing it for the first time. Before I jump into that, I do want to sort of just quickly remind everyone about during the Pleistocene maximum, the last glacial maximum that happened about 20,000 years ago or so. Most of northern North America was covered in a couple of big ice sheets. The most prominent ones were the Laurentide ice sheet to the east, so the eastern 2/3 or 3/4 of Canada was covered with that one, and a separate ice sheet, the Cordilleran ice sheet, that was dominantly sort of a big coalesced alpine glacier system. And that's what we're going to be focusing on here. I'm not going to be talking at all about the big Laurentide ice sheet, but that was by far the bigger of these two. But it didn't come in our direction. And Michael had mentioned that you've had several people talk about the ice-free corridor. There's sort of a representation on this very classic view of this about the nature of where these two ice sheets join together, and when or where there was an ice-free corridor. But that's way outside of my expertise, so I won't talk about that one either. Zooming in on the terminal region for the Cordilleran ice sheet, the Cordilleran ice sheet reached its maximum in sort of the northern tier of the Northwest, somewhat later than the Laurentide ice sheet. Laurentide was about 20 to 21,000 years ago for its maximum, and it was already retreating by the time our glacier, our ice sheet, advanced into Washington, northern Idaho, and northern Montana. And it reached its maximum around 17,000 years ago by most recollections. At that time, we had big ice sheets that flowed down, or ice tongues that flowed down through the Puget Sound, south of Olympia for the Puget Lobe, another lobe that went out the Strait of Juan de Fuca, and then calved off into the Pacific, and some other lobes off to eastern Washington, and this set up the whole dynamic of Lake Missoula and the gigantic Missoula floods that ripped across eastern Washington and down the Columbia River. And again, another fascinating story that I'm not going to even touch on. Just as a brief aside, and this is just a kind of a good for me to understand what sort of exposure to glaciers people might have had. Rebecca was going to set up a little quiz, or a poll to find out how many of you guys have ever actually been on or next to, like touched a live glacier during your experience. And I can get to see the results, and wow, an amazing number of you guys have been up to glaciers, which is great because we live in the Northwest and we can actually get to glaciers. It's kind of an awesome thing. Wow. So we've got pretty much almost everyone, with just a few people who haven't, and that's great. That's a remarkable, like even our students here at Western, despite how many of them love going up into the backcountry, have been on, not many have been on glaciers for the most part. And they're pretty fascinating things. People who study glaciers properly are called glaciologists, but I don't really do that much. I do a little bit of glaciology, but I'm fundamentally a glacial geologist, and what I study is what the glaciers leave behind. And so we're not going to be looking at any live glaciers for this talk today. We're talking about long dead glaciers, but looking at the landscapes that they've left behind. So just as setting the stage for what we're going to talk about today, as I mentioned earlier, the glacial maximum. There's my little sound effect, my one animation, because hopefully that wasn't too intense. But about 17,000 calibrated years ago, radiocarbon years and calibrated years, I don't know if you guys have heard about that much. Radiocarbon years is one of the most common dating methods that we use for dating these various advances during the late Pleistocene. But you have to calibrate the ages to real years, the calibrated or calendar years. So some of my slides will have the radiocarbon years because those are the way they were reported historically. Mostly what I'll be dealing with in the end is the calibrated, the real years. This is in real time frame, before present, okay? The BP means before present, okay? The basic idea here is that during the last glacial maximum in Washington and much of the northern Cascades, there was a series of glacier advances and retreats in various locations. The overall time period is termed the Fraser glaciation. That's the time period from about sometime before about 25,000 years ago. These are radiocarbon years here, but 25,000 calibrated years. The Alpine glaciers advanced first up in the Cascades and the Olympics. It appears that they advanced first. Then as they were retreating a little bit, the Vashon stayed, which is the Puget Lobe and the Juan de Fuca lobe coming down advanced into Washington as the mountain glaciers were retreating. Why that happened is another one of these conundrums. But again, I won't be touching on that because I'm going to be focusing on what happened after this big set of ice sheets here retreated back north of the border. And then in this time frame here was both a retreat as well as a potential readvance of the ice sheet, but only up here into the northernmost section of the Fraser Lowland. Okay, so like I said, we're going to take a look at the Fraser Lowland, which is basically considered this area up here. The border is right up at the top of this box here. And what we've got here is the Fraser River flowing out, flowing north and going out near North Vancouver. And in that time frame that we're talking about here, there was a readvance of that ice sheet. It had retreated north of the border, but it readvanced south and came all the way into sort of the northern Whatcom County region. And we're going to focus in on this last gasp event. And after this event, basically the ice sheet disappeared. It collapsed wholesale. So this was the last remnant of it before it went away completely. So zooming in yet again, here's a hillshade relief map of the Whatcom County area, and here's Skagit River down here, so a little bit of Skagit County. But we'll be focusing in on the area up here, not in the mountains. We're not going to be talking about the mountain glaciers and what they were doing at this time frame. We're just going to be focusing on the Cordilleran ice sheet, which had this series of remarkable events that happened and when it occupied and invaded basically Bellingham and Whatcom County. Okay. So the impetus for this study was this controversy that's been going on for quite a while in our neck of the woods, in no small part because of the fact that this readvance spanned the border, and the evidence for it is on both sides of the border. And normally you think, well, our border, except for during pandemic times like now, it's been pretty easy to get back and forth across the border. But dominantly geologists tend to be fairly provincial, and we oftentimes tend to work in one area or the other. And in this case, both of the main proponents of the two different ideas here work dominantly on their side of the border. So the neighborly dispute is sort of Captain America versus Captain Canuck. And I don't know if any of you guys, I knew there was a Captain America, but I'd never heard of Captain Canuck. So maybe that's my ignorance, but this is, I just sort of Googled it, and well, they came up with a Captain Canada. But that's not the real controversy. The actual controversy is a set of concepts that have proponents. Dominantly, the one north that was developed north of the border primarily was developed mainly by a Simon Fraser professor, John Clegg, and colleagues. And he published a paper on it in 1997 that sort of codified their ideas of what was going on there. And in their view of this event, and what you're seeing here in this map is sort of what they're seeing as the deposits related to two different advances of the Cordilleran ice sheet during this time interval, this sumath time interval. And they've got advances in their model. Both are relatively early in this deglacial period, before about 12,500 years ago for both these advances. And the cause of this advance, which is, again, this has been part of this controversy, is what's causing this advance. In the view of Clegg et al., it was some combination of possibly glacier dynamics, so something about the ice, like a surge event or something like that, that isn't necessarily climatically based, but it may have had a climatic impetus as well. It wasn't clear what the actual cause was because their timing suggested that it was during an interval where climate shouldn't have necessarily caused an advance by itself. And one other element of their model is that there is a sea level rise between the two advances. So the glacier advanced once, retreated, sea level came up, and then there's a second advance in that time frame. The opposing model, again, focused dominantly on evidence south of the border, was primarily been proposed by Don Easterbrook and several of his students, including Dory Kovenen. And they codified their model in a paper in 2002 that fundamentally boiled down to having mainly one main advance with several sort of recessional phases as it retreated back towards the border. Their age constraints were almost entirely post 12,500 years ago. This may not seem big to most of you guys, but there's a sort of a tight window to fit these things in. And having one that says pre-12,500 and one's post-12,500 is a pretty different distinction. And part of that distinction was that Easterbrook and his colleagues have sort of mostly claimed a climatic cause or inferred a climatic cause for these advances rather than glacier dynamics. And one of the key things that we'll talk about for a fair bit coming up here in the talk is that their advance was preceded by some dramatic sea level fluctuations during this Everson interstate. An interstate is a period where the glaciers are retreated some. So before their glacier advance, they had a couple of very extreme 100 to 200 meter rises and drops in sea level within a 1,000-year window. So something very, very dramatic. And that was the main thing that got me involved into this, because this what Don has termed yo-yo tectonics was something that I couldn't quite wrap my head around. So I just wanted to see, okay, is there a way to resolve these? Just to sort of go into the crux of this explanation, the concept that of this yo-yo sea level interpretation, we have to go to the Everson Type section. This is a section that Don found way Easterbrook back when he was getting his PhD, he found this amazing exposure along the Nooksack River, and he defined a series of units there that were all in his mind sort of interstadial. So they're part of this Everson interstate when the glaciers were not right in this neck of the woods. And what he's got here is he's got two different what are called glacial marine drifts, or GMDs. And these are marine deposits deposited out in front of an ice margin. So where you have a glacier flowing into the ocean, dropping icebergs, calving icebergs off, and having lots of meltwater come out into a raised sea level. He's got two different layers, a lower layer and an upper layer in this big exposure. This is about a 50, 60 meter high bluff. So some big packages of glacial marine drift. So two periods of glacial marine drift with icebergs and high sea level, but it's divided by a clear sandy unit called the deming sand that he has documented rooted stumps in, and that this is, and his interpretation is that this is a fluvial sand. And to get rooted stumps, a forest growing there that is then buried by fluvial sand, you've got to have this above sea level. So you've got below sea level, above sea level, below sea level in this sequence. And that is what led Don to make this interpretation of these big swings in local sea level as recorded in this bluff. There are other deposits that he has correlated to this, but this is the one that is by far the highest elevation and the one that requires really big high swings up here in terms of the height that the ocean got to relative to modern sea level. Okay, so this is sort of the crux, and this sort of drove me to think of, well, we really need to reinvestigate this, because if we can somehow find evidence that maybe one of these isn't a GMD, or that these rooted stumps aren't actually in place, that maybe they floated out into an ocean and sunk, or something like that, then you can get rid of the double hump here, and just having a single hump is something that's easier to deal with. It's the double hump thing that's a really hard thing to deal with in terms of sea level change, rapid sea level change. So I just want to take a quick aside, because again, I'm not sure how much people know about relative sea level changes, because it's a big part of this story, and we want to sort of have a sense of how can you change local sea level fairly dramatically. And we're not talking just centimeters or a few meters, we're talking hundreds of meters potentially with this. So we've got to sort of have a sense of, okay, what ways can we have big sea level changes in a local region? So there's three main ways I want to introduce to you guys that we can change sea level at a single locality. One is eustatic, which is basically a change in global sea level, because global sea level, if it changes enough, will affect anywhere on the Earth, including Whatcom County or Port Townsend or wherever you want to think about. And so what I've got here is a graph of the sea level rise that followed or came on the shoulders of the ice sheets disappearing at the end of the Pleistocene. And this shows that basically back during the glacial maximum, about 20,000 years ago or so, Most sea level records have global sea level about 130 meters lower, so about 400 feet lower than it is today. And then it came out of it and then rose up to basically where it is today by about 8 or 9,000 years ago. It was up to near modern, and there's just been little wiggles since then. And that is dominantly because of changes in the global ice volume. So big ice sheets melting away, the ones up in Canada melting away, ones in Europe melting away. There are changes in sea level because of ocean temperature changes, but those are pretty minor compared to this big ice sheet melting. Okay, so that's one, that's eustatic sea level changes. Another one is called isostatic changes in sea level, and those are related to loading or unloading the crust of the Earth. And in our case, what we're focusing mainly on is ice sheet loading. So if you plop a big ice sheet, or you have an ice sheet advance out across the border into Washington, into northwestern Washington, that big ice sheet will sink the crust. It's heavy enough that it actually sinks the crust down, and the mantle flows out from below the crust, and you actually have a substance of the land surface because it's covered with this big heavy weight. The sinking, because ice is about 1/3 of the density of the crust, whatever the thickness of ice is, you can have the potential for sinking it up to the crust up to about 1/3 of the thickness of the ice. Around Bellingham, our ice got up to about 2,000 meters thick or so. So that has about, you can almost put 600-700 meters of isostatic depression locally here in Bellingham. And that's a lot. So that's even more than the eustatic, the global sea level changes. So you could sink it even further down than the global sea level is lowered. Those are the two that we know happened here in Puget Sound. That there's no debate about that. Everyone knows both of these have affected our local sea level. But there's one other one that will affect sea level or can, depending on where you are and what the tectonic conditions are. But that's tectonic uplift or subsidence. I just threw this picture, and it's kind of a grainy picture. I don't know if you guys, how well it shows up for you guys. But this is it's a nice picture of a series of uplifted shorelines in the North Island of New Zealand. And what it shows here is a series of old beach ridges or beach cliffs, in the case of the one back here, that were record the level of sea level at this site at various times in the past, 5,000 years ago for the upper one, 2,300 years ago for the middle one, and about 1855 for the lower of those three. And each one of those represent a different earthquake uplifting that portion of the crust there. So you're seeing a sort of a gradual but steady uplift of things that were underwater are now above sea level. Okay, so tectonic uplift and subsidence is another key issue to consider, and we do have that in the Puget Sound as well. Okay, locally. So let's get back to that crux of the yo-yo sea level interpretation, is that we've got not just one sea level high stand and low stand. We've got, according to the yo-yo interpretation, Easterbrook's interpretation, is that we've got two marine deposits separated by a subaerial fluvial deposit. And if valid, and these things go up to about 100 meters above sea level, plus some extra to go over the top of this, you come up with this idea that, okay, sea level has to go up, and down in this really rapid fashion in about 1,000 years. Okay. The key about this is because of the double hump here, that requires eustatic, isostatic that we know are happening, but it also requires tectonic uplift. You can only get really one hump here with just eustatic and isostatic. But the tectonic uplift that's required to do this would be pretty much almost unprecedented in terms of both its rate, its pacing, its rapidity, but also in terms of the magnitude of going up or down by 100 meters or 200 meters. Very, very unprecedented in terms of my understanding of what's possible tectonically. So that led me to say, let's reevaluate this. Is there some way we can reevaluate the deposits that have been in this sort of part of the center of this controversy? So the key things here, the sumath conundrums, what I tend to refer to it is number one, is there a way that we can resolve the two disparate interpretations on either side of the border in terms of, can we refine the timing of all these different events? Because timing is a key element of the controversy in this area in terms of when was sea level high or low? When was the ice sheet advancing or retreating? These are things that we can address, we can test. And then also, how did those ice sheet fluctuations of advances and retreats interact with sea level changes? Okay, because again, those are key aspects of the differences of opinions between the main proponents. And then finally, in my mind, is there an alternative to this, the yo-tectonics concept that just wasn't satisfying to me. It didn't make sense in terms of the sheer magnitude and rates that would be required. So let's go check that out a little bit here. First thing I really did when I started diving into this was to go say, okay, let's go double check and make sure that those interpretations of the Everson type area are reasonable and do they make sense. And so I've gone back numerous times here, and the type area is in this outside of a meander bin along the Nooksack. This area was completely flooded this last week too, by the way. If anyone ever heard about the flooding we were having, this place was completely swamped through here. And I'm guessing it probably has refreshed this cliff, this exposure here, but this exposure is kind of a wild place. It's our miniature Oso. It's similar to Oso in a lot of ways in that it's similar types of deposits and same sort of setting. It's a river undercutting a cliff of dirt, basically, of glacial sediments. And it's eaten away several houses. This house is now gone. That's their garage down the hillside there. That happened back in the mid-2000s. Here's that house just before it collapsed. It's kind of a sad story. Those folks, when they bought the house, apparently had no idea that the river was even that close to them, because they had about 200 feet more space before the bluff. And this bluff got eaten back in a matter of about 5-6 years or so during one particularly active interval. It's also a very mighty place to work. This is it's me, but with a couple of our Canadian colleagues, John Clegg among them, who I've worked with a fair amount. He's one of the proponents of the Canadian model. So I dragged him south of the border. And he got stuck here for a while. It's an amazingly mucky area at this time of year when the rains are around. It dries out in the summertime, as you can see on this side, but it's a mess when we're trying to work in the winter or spring. But the key thing here is that because the river's undercutting this bluff, we get constantly refreshed exposures of this of the sediments here, so we can usually get access to the sequence. And as Don has long described it, it does have a very distinct set of beds here, of layers of a lower, what's called a diamicton, a mixed muddy, mud-rich sediment down here with large clasts in it. Separated, there's a nice bedded sand right above it, a dark bedded sand. And then there's an upper diamicton, an upper unit of really mixed stuff, that both of which look a lot like what you'd expect a glacial marine drift to look like. But let's go take a look at so if you remember what I was talking about, I was wondering, okay, is there a way we can get rid of one of these glacial marine drifts, either this one or this one, and turn it into something that's not submarine? Or can we take this deming sand and find out that, oh, these root stumps aren't actually rooted, they floated in. So this is a marine sand, so it's just marine, marine, marine. Either one of those will help us get rid of one of those humps. And that would make a much easier situation to explain. Go to look at the sand, the deming sand up here. There's ways to get up there. It's halfway up the cliff, but there's places where it's not a cliff and you can get up there. And it is a beautiful sand. It's really nicely bedded. It's got beautiful laminations in it. It's got lots of organic stuff in places in it, peaty areas. And in fact, it does have what I would say are convincingly rooted stumps. That's a root coming out of a tree that's in place. And so I think there's almost no question. There was a forest growing here and it got buried by this sand. A fluvial origin is one option, maybe a deltaic sand is another option. But it's buried by sand. So this was subaerial. So then we go to, is there any chance that either one of these supposed GMDs are actually not marine? And so one of the things I did a number of years ago is I spent about a week and a half every day coming out here, digging around, looking for evidence of glacial marine, of a marine origin for these things. And the key thing, the key evidence for marine origin is finding marine organisms preserved in it. And if you go to this upper glacial marine, or this upper drift, which is termed the Bellingham drift, there are, especially in the lower end, right above the sand, the deming sand, there are in local places abundant tiny little articulated shells. Articulate means that they have both bivalves, and they appear to have been living in the mud and got buried. And that was really clear evidence that this lower portion, at least, of the this upper unit is a marine deposit. I think that's probably indisputable. And it wasn't like these were transported in by the glacier or something else like that, by a glacier. They're not sheared up or smashed, they're intact. So that's definitely convincing that there's a marine deposit up here. So how about the lower unit? Well, the lower unit's a lot harder to get clean examples of, because so much of this stuff on the cliff is stuff that's fallen down from up above. And both of these units, but the lower unit and the uppermost unit, both look very similar on the surface because they're fine-grained muddy deposits with coarse clasts in them. But when I spent so much time cleaning off exposures here extensively and digging in there, making sure I wasn't just sampling the slough from above, this hill slope slough, which a lot of this stuff does include clamshells. But whenever I dug in deep into where I was into the original deposit, not the stuff that had fallen down from above, I haven't once ever found a shell intact in any of those. So my alternative interpretation is this lower unit not a glacial marine drift, but actually a till. So something deposited by a glacier, which is another thing that looks exactly like these deposits. The glacial deposit, the till, doesn't necessarily need to have clams in it, wouldn't have clams. So if we take a look at Don's original section here, what my investigation of the field called into question are the rare examples that Don found, is it feasible that those are actually not in place, that they were things that were part of the slough from up above, and which is almost indistinguishable from the stuff down here, except if you dig in deep and make sure you're in the original stuff. The other thing I haven't had a chance to mention is that I also looked up near the top of the column, and I couldn't find any intact shells up there too. The upper half of this really didn't have any shells in it either that were intact. There are little bits and pieces here and there, but nothing much else. And so with all this different work, we came up with an alternative interpretation for this. Is it feasible that the upper part of this is not a glacial marine drift, it's a till? There is a glacial marine drift down here right above the deming sand. I completely agree with that. But is this lower drift down here a till also? So we have a till, a glacier advance, glacier leaves, forest grows, something happens, you bury the forest with the sand, but that sand gets inundated by the ocean. So a sea level rise buries this area or covers this area. You get glacial marine drift. The drift is related to an advancing glacier somewhere. And then is it feasible that glacier gets advanced enough that it actually overrides the area here? And you have a till at the top. Okay, so that's sort of the general sequence here. And if I present that in my own graph here, so what we've got here is a Colchian till, not a GMD, deming sand, Bellingham, a GMD, but then followed by a till. What that allows us to do in an age, and this time I've reversed the age, so pardon me for that, but it's going from older to younger this way, is that the area is deglaciated, sea level starts coming down, but goes back up for just a short period of time and then comes back down again. A single hump, we can explain that with just isostatic and eustatic sea level changes. We don't need tectonism, and especially some really remarkable tectonism. So one question here is, is there a way to do that? Well, remember the isostatic, the weighting by the ice sheet causes the ice sheet to sink, or the crust to sink, and it's coming up from a much deeper level. So initially, when you first deglaciate, even though global sea level is lower, the local land crust is even lower than that. So sea level starts high, and then is there a way to reverse and have global sea level outpace the isostatic rebound? And there's a possibility, because right in the right time frame, there's this thing called, go back, meltwater pulse 1A. This is the single biggest leap in global sea level, eustatic sea level, in the entire deglacial period. It looks like it went up somewhere between 20 to 30 meters in as little as a few hundred years, or maybe even less. They don't know what the source is for this. There's lots of hypotheses about that, but that this happened is quite clear. And it happened right in the time frame based on our radiocarbon dating from that type Everson area, that right between two different glacier advances, there was that meltwater pulse came in. So could that be our explanation? So the key thing here is that this explanation doesn't require a yo-yo. It just requires eustatic and isostatic uplift. Okay, so that's sort of the addressing the stratigraphic arguments. But let's go take a look at Lidar. And Lidar adds to the story really nicely in a certain way. And so I want to introduce this a little bit to you guys, and it's what I refer to fondly as X-ray vision for geomorphologists. And Ralph Hugger can tell you all about that too. He's much more of an expert on it than I am. But I have my second little poll for you guys is how many of you have heard of, looked at, or used LIDAR? And I'm guessing based on the other responses, you guys have probably, most of you guys have probably heard of it at the very least, or use it often. Great little polls going. Yeah, okay. So we're getting, yeah, quite a mix here. So some of everything from never heard of it to use it often every day. I definitely am one of those who uses it every day. And for those of you guys who aren't aware of it, if you just Google WAD DNR LIDAR, it'll send you up to their LIDAR portal, and they've got an amazing array of maps, LIDAR-based maps that you can download and goof around with if you want to, just sort of explore your terrain a little bit. Why they're so important though, is because it's a super fantastic new technology that's been developed over the last 15 to 20 years that really is allowing geomorphologists in particular, geologists in general, but geomorphologists in particular to see landscapes like we had never seen them before. So what is it? Just for the people who don't know about it or don't know much about it, LIDAR is an acronym for light detection and ranging. And it's basically this idea that you fly over landscape with an airplane that has a laser scanner in it. That laser scanner sends out pulsed laser beams at the ground in really rapid succession, thousands of pulses per second as it's flying along. It's got a very high precision GPS, so it knows exactly where the airplane is and exactly where the ground points are, where all the returns are coming from. And that laser beam just coats the landscape, just like any other type of scanner you guys might know of. And the great thing about LIDAR is because these laser beams come down and they will hit the leaves and needles and whatnot of trees and buildings, but at least in terms of vegetation, there's parts of the laser beams that go all the way through all the leaves and everything else, hit the ground and bounce back. And so the great thing about this is you'll get a data set. The laser beam cloud will include all sorts of information about the trees, but you can effectively clear cut a terrain and just see the ground, and that's it, at a resolution that is unprecedented in science before LIDAR came out. So just to give you an example of what this looks like, here's a forested region. This is actually down near Lake Tahoe, another place near and dear to my heart. So when you just see an air photo of it or a topo maps are usually made off of air photos like this. So you can see the ground in places, but a lot of it's covered by trees. If you look at sort of the raw laser scan that includes the trees, it looks not too different from what you've got there. You've got lots of trees. You can see the ground in places, but again, the trees are kind of in the way. For us geologists, we want to sort of clear cut those trees out of there. And the great thing about these data, because they're digital, you can strip away the trees. There's programs to strip away the trees and give you what's called a bare earth figure. And in this case, what we've got here is we can see, I don't know if you guys can see, is this stripe across the landscape here. That is an active fault on the west side of Lake Tahoe that was basically unmapped before the LIDAR came out for this area because we could strip away the trees. Even though you could walk across this, you couldn't connect the dots. Oh, that's a fault scarp. That's not just a little lump or bump in the terrain. And LIDAR has revolutionized geosciences, I would say. I'll give you another couple of examples. An air photo. This is a DEM, a 10-meter DEM that's based on topo maps. This is sort of near Bellingham. And here's the LIDAR. So, the difference is stark, to say the least. So what's the value in our case for this problem? I'm doing time-wise. Okay, doing okay. So what's the value of LIDAR? So this is a LIDAR hillshade of Western Whatcom County. The border is just up near the top of the screenshot. Let's go zoom in on some of these scenes and see what this allows us to see in terms of the glacial geology, the stuff that I'm most interested in. So we're going to zoom in here to South Whatcom County, just south of Bellingham. Bellingham's right in here. And this is Lake Whatcom and Lake Padden, for any of you guys who know about it. We're zooming in on Lake Padden. It's not blue here, but that's it, the flat surface. And this is I-5 going up through Bellingham, up that direction. And so one key thing here is a quick quiz for you guys. Can anyone see the moraine in this image? There's a small little glacial moraine, a place where the glacier stopped first, or built a little moraine, a little hill of till in this image. And no one knew about this until the LiDAR came out. I won't keep you, I know you guys can't respond easily at this point, so, but probably in chat, which I can't really see at the moment. But basically, the moraine wraps across the hillside right here. It's just, I'll back up here. It's this little tiny squiggly ridge here, comes right over through here. And that little squiggly ridge is a place where this Cordilleran ice sheet hung up for a little bit and may have readvanced there, or it was during recession. It's not quite clear what it was doing, but it's a little tiny moraine that is sitting right in this area here. And the glacier was going right up against Lake Padden, but didn't actually cover Lake Padden during this interval here. If we zoom in to one part of that, so here's that little squiggly ridge here, coming across here. And this is a very popular mountain biking area. This is a Galbraith Mountain for any of you guys who know about that for mountain biking. And there's a place where there's a pipeline road that goes right through the middle of the moraine. It's one of the few places you get an actual exposure into it. And here's what that moraine looks like on the ground. Got Sean Lahuzen, who's a famous, sort of famous, at least in small circles, former Western student, and he did some work with me on this. But that moraine is just a little tiny hill of dirt in amongst thickets of trees, but the LiDAR allows you to see it in ways you could never see before in terms of its continuity and its extent. Another set of, so that same moraine goes into Lake Whatcom further north and then climbs out again and comes back across Squalcon Mountain here and wraps around the hillside. I don't know if you guys, again, depending on your screen size, you may or may not be able to see this. It's a tiny little thing, but it's quite clear and continuous, wraps across the hillside and forms a little loop here just south of what's called Squalcon Lake, and then goes back up into the hillside around this way. Squalcon Lake's really interesting because it's sandwiched between that moraine, so one port location of this sumath glacier advance, and another set of bigger moraines that Mount Baker Highway trends along that show up as these big long ridge lines through here. Those are all glacial sediments formed by a glacier that flowed this far south and then backed up, retreated some, and then formed a new moraine here. That moraine impounded Squalcon Lake, and so gives us a sense of, if we could core that lake, we might be able to document when the glacier left this area and when this glacier was emplaced. And so I went out there with a number of students a number of years ago, recovered a sediment core, about an 8-meter sediment core. And this is just a section of it. What we're seeing here is this is a sort of it's called a magnetic susceptibility record for that whole core through here, going from 0 down to about 600, around 6 meters depth or so. And mostly it just records monotonous Holocene lake mud. It's really organic rich mud with not much going on in the whole Holocene. But there's a few big blips in that susceptibility. This is where the sediments are more clastic rich and they have more of a magnetic signature in terms of being able to measure. The lowest one here, or the highest one, is Mazama ash. So that's from Crater Lake. It's a nice little timeline for us. But the area I was interested in is going back here. There's 3 big pulses here. There's a bottom pulse of very classic low organic rich sediments. This looks like rock flour, and in the core, that's this section right down here. This is all rock flour dominated. The only way that lake would get that was with a glacier sitting right nearby. The glacier retreated back. There's an organic period where the susceptibility drops, the organics go up. That's a non-glacial period. And then that's cut sharply by another gray rock flour period, which is the second peak here. And then finally, there's a weaker period, peak up here that's not really a rock flour, but it may have been some sort of a dusty period. The key thing here is the dates from the non-glacial periods, these radiocarbon dates from these organic layers, give us an inference that the lake existed, came into existence shortly before 14,200 years ago. The second pulse of glacial flour was 13,000 years ago. And then somewhere far away, there might have been some sort of other event going on about 11,000 years ago. Okay. So that tells us that this lake was formed shortly after 14,200, and that second pulse, the most likely candidate for the second pulse of rock flour is the emplacement of this moraine here, right at one end of the lake. And the glacier retreated from that by 13,000 years ago. Those are both older than was originally proposed by Eastbrook, or even by Clegg for that matter, but they're more in line with what Clegg had interpreted. So that's, in a nutshell, that we've got some age constraints on when the glacier was at its maximum, and it had a series of advances before 14,000 years ago, somewhere between 14 and 13,000 years ago, and then maybe something very late in the game. So like 3 main phases. But what about sea level? And the Lidar helps immensely with the sea level story as well. And we're going to zoom in over here to the west near Ferndale. Here's I-5 again, coming up to the north. And Ferndale is right down here. And again, this area was completely swamped out, or parts of this, just last week. So we've got the floodplain coming through there. But what we've got here to the west of Ferndale is what's called the Terrell Highlands. And it's got 2 main types of morphology here. The highest parts of the highland are really hummocky, lots of very fine, irregular hill structure that's really rough. You also have numerous gullies that come down and just stop suddenly against this, what is a much smoother terrain down here. And the smoother terrain has really nice, prominent, little subtle benches and places on it that are nearly horizontal, wrapping around the hillside. And there's a whole series of these things. They're like staircases. And so the basic interpretation on these is that these staircases are recording old shorelines, raised shorelines, at the end of the Pleistocene, that formed during the end of the Pleistocene, when the eustatic sea level was low, but the isostatic sea level was high, or the crust was depressed, so local sea level would have been high. The highest of these shorelines in this one area here is right up here. It's about around 100 meters here. It gets, as you get up closer to the border, it gets even higher, up to about 120 or 140 meters. But this one location, that's the highest shoreline right there. The interesting thing is that it is truncated. This red line is glacial sediments from the highlands. There's all a bunch of morainal material up here. The morainal material drapes over and truncates that high shoreline. But as you step down, you get another shoreline. The white lines are all going to be shorelines that comes in and truncates that glacial margin right there. That glacial margin, or that sea level, is then truncated in turn by yet another younger moraine. So this moraine here that has never, this one reaches below any of these shorelines. So but it still has that subaerial rough surface. It could only have formed if sea level was lower to an extent when the glacier was forming this, and the glacier would have been over here covering Ferndale. So it's flowing this direction towards Bellingham Bay. You follow that moraine down, it gets to the point where it's truncated by oak. Here's another shoreline right here, these nice flat surfaces, and that shoreline goes inside that moraine. So the glacier had to have been gone, retreated back somewhere to the north a little ways for the ocean to come in here, but that ocean sea level is lower than it was when this was deposited. That shoreline is in turn inset by yet another little tiny subaerial moraine inset down here, much closer to modern sea level. And that little squiggly line there, if I back this up, that little squiggly line, if the ocean had ever covered that, it would have smoothed it out completely. It isn't smooth, so that means it was never below sea level. So that one in turn is cut by yet another one of these inset shorelines, which is then truncated by another shoreline, moraine position, which is then inset by yet another shoreline. And this shoreline here is only about 4 to 5 meters above modern sea level. So while the glacier was sitting there fluctuating back and forth and maybe slowly retreating, the whole area was popping out of the ground. So it was happening simultaneously. It's a really amazing record of cross-cutting relationships. Really quickly run through what's going on in Bellingham proper. We just zoom in here just because this is sort of near and dear to my heart, living and working right near this. We've got a couple of very unique landforms here as well. We've got this really flat area that most of sort of downtown Bellingham is built on, and a lot of the houses near downtown. Nice flat surface that is composed of gravels and sands, fluvial gravels and sands. It looks all the world like a delta. And sure enough, looking just upstream from that, there's this big, massive channel that comes up through here. And that massive channel terminates really abruptly up in this neck of the woods into a couple little channels, and that's about it. And what it really terminates into is a set of moraines. There's our Squalcon Lake right there. There's a set of moraines here that wrap around. You can trace them on the Lidar through here, and they come all the way down along the side of that delta. So what they imply is that the ice at this time was sitting right here just outside of Bellingham. There was a delta forming here, and that there was an outflow of meltwater coming out of that ice sheet down this channel and going into a slightly higher sea level, about 30 meters above modern, right there. And so we've got this nice little story right here in Bellingham in terms of ice position, big meltwater discharge, and Bellingham being built on a ice age delta. So let's put it all together really quickly so I can wrap up. The basic story that I've come up with my colleagues is that outermost moraine, we call it the pad moraine. This is something also that Ralph Hagerud and Dory Kovanen have mapped as well. So, and they have a beautiful map out, by the way, that you guys should know about. That maximum position of possible sumath ice might have looked something like this. We don't really know for sure what it was doing over here because the moraines are obscured, or even over here. We know it's mostly from where the moraines are over here in the area just west or east of Bellingham and out here near Squalcon Lake. But it was a pretty big advance that came. Glaciers had retreated north of the border. They re-advanced here. This probably happened sometime about 14 and 15,000 years ago. The glacier kind of had to retreat somewhere in there in order to get that big burp in sea level, local sea level that I suspect was related to that meltwater pulse 1A. And if we put about 110 meter sea level around the landscape here, what you see is most of Western Whatcom County was underwater, including our Type Everson site here. Then the glacier re-advanced into that neck of the woods, forming the Bellingham drift. And that re-advance is the one that would have shut off Squalcon Lake down here and formed a series of moraines that come into Bellingham, as well as up here in the Terrell Highlands. Local sea level is higher then still, but it was going down. And this is that period of interleaving moraines and shorelines as sea level is going out, as the glacier is sort of fluctuating back and forth. And then eventually the glacier retreated all the way back up towards Canada. And there seems to be a final Canadian invasion up near Sumath. It's a nice discrete set of moraines up here, and that's sort of the last moraine set that seems to be associated with this. And this one may have been one that was somewhere around 12 to 11,000 years ago. Okay, but we don't know. The dating on that one is still up in the air. I would argue at least. Okay, so really quickly, take-home messages here. I think I'm just about on time here. First and foremost, landscape of Western Whatcom County is really remarkable. I got to say, when this LiDAR started coming out, I was just like, wow, there's so much to this stuff. It's pretty awesome. It preserves a really remarkable interplay between glacier advances and retreats and sea level going up and down in rapid succession in a way that I have not heard or seen about anywhere else in the world. There's a eustatic inundation in glacier advance for sort of what I call main sumass, isostatic reemergence and glacier retreat, sort of working in tandem. And the fact that they seem to be working in tandem begs the possibility that maybe part of this advance is related to the sea level coming up, allowing the glacier to slide easier out into the bay and advance. Then as the rebound drove sea level down, the glacier started getting hung up and started retreating again. So maybe there is a possibility that this is more of a dynamic response of the ice sliding rather than climate change. All occurred within a few thousand years or less at the very end of the Pleistocene. So it's a very unusual period where things are kind of going crazy, it looks like. LiDAR is absolutely key to this whole story. This would not hold together without having all the LiDAR in there to hook together these disparate stories that you might come up with separately. Just to sort of reiterate some of the key things here, findings that I've made and other people working on it like Ralph. The outermost moraine is 10 to 20 kilometers beyond what was previously mapped by either Clegg or Easterbrook. And that's the LiDAR that allows us to see that. That moraine is small but continuous, goes all the way from Lake Padden to Squalcon Lake, but it's still a key to the whole story. formed about 14,500 years ago, which is quite a bit earlier than previously considered. The maximum sea levels appear to have happened shortly after that glacier retreated, 14,500 to 14,000 years ago. That may relate to meltwater pulse 1A, this global rapid rise in sea level. Again, that needs to be teased out a bit more. The subsequent, what I call the main sumath advance, occurred just as sea level began to retreat, a little less than 14,000 years ago, but still earlier than previously considered. Relative sea level, RSL, was near modern by 13,000 years ago during the sumath. So this is a really rapid change in local sea level, going from above more than 100 meters above sea level to down to near modern by within about 1,000 years. That's a really remarkable rapid change in local sea level. And the final thing here that I'll finish with is that these new constraints, even though they're a bit earlier, the timing is a bit earlier than previously considered, they're much more consistent in general with the Canadian interpretations from north of the border. And I think in future, I'm hoping to hook together with some of the Lidar that's being published now for Vancouver area to sort of tie this whole story together across the border. And so I'll just leave it with a little picture of, yeah, Captain Canuck looks like they're sort of standing a little bit taller after this, but there's still a good story on the American side that we're still working on. But it's been a fascinating study so far, and I'm still working on it. But hopefully you were able to follow along with most of that. It's kind of a lot of balls in the air, but it's a really interesting story, kind of an amazing time period. So with that, I'll end right there, and I'd be happy to entertain any questions. I just want to thank all the various colleagues who helped me, most of whom are Western students, but John Clegg from Simon Fraser's clearly was a big influence on this whole thing. And my email is up here on the screen if you guys care to email me about any questions you might have to.
Thanks. Thanks, Doug. We'll give you a virtual clap there. So, right on time, lots of technical content. Do we have any questions? I see one or two popping in here. So I'll take the first one. Rebecca can take the second one. Carol Tepper says, what are the maximum rates of isostatic adjustment and the maximum total amounts, not just for the planet, not just Western Washington? In other words, are these in the ballpark for the world?
Well, so the isostatic changes in sea level have to do with local loadings or unloading. And so for the types of changes we're seeing here, it takes an ice sheet sitting on top of the landscape for a little bit. So you have to be someplace where a big ice sheet would come in. Little mountain glaciers and stuff like that don't do much, but it's the big ice sheet. So most of the world doesn't undergo these sorts of isostatic responses because they don't have ice sheets, or they didn't during the Pleistocene either. It's only these places that have ice sheets that get the isostatic response, which is, again, that's the local loading of the crust. One of the interesting things, and this is something you can see in the geology as you go further south into the Puget Sound, for example, because the ice sheet was there shorter for a shorter time period than it was in Bellingham, and the ice sheet got thinner as it got towards its terminus down near Olympia. The isostatic depression down there was quite a bit less than it was up here. In fact, it kind of almost disappears by the time you get down a little bit south of Seattle. And that's because the magnitude of isostatic depression and eustatic changes, the global sea level, sort of are on par with each other. It's mainly where we had really thick ice, like we did up here in the northern portion of Washington and Salish Sea area, where it's quite big. I actually don't know, like, I'd be curious on the Kuiper Peninsula, like what the isostatic difference is there. I'm sure it's quite a bit less than it is in Bellingham in terms of what the depression was or the local sea level high was. So I'm not quite sure if that addresses the question. That's the isostatic response. That's a local thing. The eustatic is the global one, and that's the things that get people somewhat concerned are things like that meltwater pulse 1A, where global sea level went up by 20 to 30 meters in very short order. It was almost certainly some sort of calving ice sheet margin collapsing into the ocean, or a big burp of a meltwater lake somewhere.
There's one point I want to make is that there's been some pretty good studies of isostatic rebound from deep lakes like Lake Bonneville. And that occurred, there was a
Right.
great response between the flood event and the establishment of Provo.
Yeah.
And
Yeah.
not only that, you can see how far it goes into the mountains. You can see the lateral extent of the rebound and the shape of it too.
Yeah. Yeah. So loading by lakes, big lakes also will give you a nice depression. That's a really good comment there, Michael.
Rebecca, what do you got?
Yeah, another question for you. So are sediments of the glacial outburst floods down the Fraser related to the Deming sand?
No, that's a good question. I don't think so. So if I go back here and get one of my this thing here, so that there's the ice. I assume the outburst flood that the questioner is asking about is one that made this. I don't. This might be too small for some of you guys to see, but there's a series of dramatic channels right outside of the very final sumath moraine. There's a whole series of dramatic channels that appear to be related to an outburst flood that came out of the ice sheet right before it just melted away and disappeared. There's actually similar channels just north of the border up along the Fraser River itself that appear to be similar in age. And John Clegg, my colleague, just came out with a paper about those, describing those. And I forget, I think it might have been Quaternary Science Reviews. I'm not sure which journal it was in. But that outburst flood clearly would have had a dramatic effect on sedimentation out in, say, Bellingham Bay or up towards the Fraser River. But as far as I know, no one's cored into those sediments to find that level of sediments. The type area for the deming sand is over here, and the timing isn't right because I would argue the timing's not right for that outburst doing it because number one, it looks like the age constraint we have for this is that this is around 11 to 12,000 years old, and the deming sand is closer to 13 to 14,000 years old. So it's quite a bit older, I think, than this one would have been. The other problem about the deming sand being related to an outburst flood from up here is it's dominated by dark, what looks dark sand. The sand is really dark, and it looks like it's dominantly made up of Mount Baker andesite. Material. So there's a concentration of stuff coming off Mount Baker. So I suspect the source of that sediment is from Mount Baker rather than from the Cordilleran ice sheet, which has a lot more granitics in it, for example, things that we wouldn't have coming out of Baker.
Okay, I'll take the next one. John Karachewski says, did the latest glaciers that covered Bellingham flow out of the Fraser River watershed?
Yeah, so, this is the source of the ice here is something it's a little bit uncertain. I know I heard Ralph Hager give a talk a while back, and I'm guessing he's permanently muted still, so he probably can't respond, but he had a proposal that it came out of one of the tributary drainages to the Fraser, not down the main Fraser itself, that the source of the ice was coming almost straight out of the coastal mountains rather than down the Fraser proper as the primary source. And I don't know if Ralph's ideas on that have changed at all. I have not spent much time at all looking at any of this stuff further north. So I will apologize. I don't know what the ultimate source of the ice for this readvance was. But it was clearly north of the border, but whether it was started somewhere further up the Fraser River proper or maybe just out of the more local mountain, it's not clear. At least I'm not clear on it.
So Rich is just asking for a follow-up or a clarification because he missed the beginning. What was the estimated range of ice thickness near Bellingham and Puget Sound?
Yeah, so Bellingham, the general thinking is that it was around 2,000 meters thick or so at the maximum of the Puget lobe and Juan de Fuca lobe. This is north of their divergence there. So it's basically the ice sheet when it was at its maximum coming through Bellingham was probably close to 2,000 meters. And the best constraint on that is that if you drive up Mount Baker Highway to the very end of the road up at Artist Point, which if any of you guys haven't been up there yet, you should go up there. It's pretty awesome, fantastic views up there in the summertime when it's open. But there's striations that go right across the crest of the ridgeline there between Mount Baker and Mount Shuckson up near Table Mountain. And those striations are related to the maximum advance of the ice sheet. The ice went from north to due south across that ridge. It went right down to the Nooksack, right up and over that ridge, and down into the Skagit without even having a blip. And that the ridge that lines up there is up around 4,500 meters to close to 5,000 meters, and the ice had to have been quite a bit thicker than that to make it over that ridge so cleanly. And so the thinking is it's closer to 6,000 feet plus or 2,000 meters or so. But we don't know exactly how thick it was right over Bellingham, just because there's nothing was sticking out of the ice down here.
And the modeled thicknesses in around Port Townsend are about 4,000 feet or 1,500 meters at the glacial.
Yeah, I actually got a question from someone recently from down near you guys. That I don't think he's part of the Quimper Society, but he was asking about how high the ice sheet got up into the Olympics. Because it ran into the Olympics, got split, and would have filled up against the Olympics where it was splitting into the Juan de Fuca and the Puget Lobe. And I haven't looked down there in detail, and I'm not sure how well defined the upper ice margin was at that point. But with LIDAR, I'm sure we could probably figure it out pretty readily. I'm sure Ralph's probably looked at that stuff before.
Okay, Paul Bellinger has this question. Let me see if I can summarize it. Wasn't much of the Puget Lobe in southern Puget Sound actually isolated from the marine realm because of the Straits of San Juan de Fuca? Lobe was grounded and didn't allow the marine waters below the ice sheet, as well as the fact that sea level was 150 meters lower despite glacial loading. So that's a long question.
Yeah, I mean, I think the most thinking is, and again, this is based on both the sedimentology as well as sort of the landscape itself, is that once the ice sheet impinged against the Olympics as it advanced into both the Strait of Juan de Fuca and the Puget Lowlands, that the ice effectively sealed off the marine waters from it. And so from that point on, because the Puget Lobe stretched from the Olympics across to the Cascades, that all the meltwater there would have formed a lake, basically out as sort of a proglacial lake as it advanced out and southward. And there's pretty good evidence for that in the sense that there's this one bed down from sort of Seattle southward called the Lawton Clay, which is this glacier lake sediments that the glacier then advanced over as it kept going further south. So it's pretty clear that was a freshwater lake once it sealed off against the ice sealed off against the Olympics. During retreat, that at some point, as the glacier retreated backwards, that seal against the Olympics would have been unsealed. And in general, there's a sense that there would have been an inundation at that point. I am not as familiar with the relative sea level evidence down that far south in terms of, was local sea level higher, like near where you guys are, Port Townsend, initially, and that the sea water would have invaded at least parts of the Puget Lowland or not. I'm not sure. I think it did to some extent, but I'm not sure how much higher it was at that level, that farther south.
Okay, thanks. We don't have any other questions on the chat board. If you've got something, oh, wait.
Rebecca does.
I have one more. So it's just me summarizing a couple of comments that have come in, but folks were really excited about the LIDAR imagery and how you're able to make some pretty big inferences at the landscape scale from it. And I love, thinking about LIDAR as X-ray vision for geomorphologists. That's really fun. And I guess just like looking to the future, do you anticipate any advancements in the LIDAR technology or other technologies that could help to tell more of the story?
It's a good question. I think there's one thing that's becoming really useful. It's not so much an advance in technology as much as just funding, because so many groups are realizing how valuable this sort of data is. But it's the idea of repeat LIDAR, where you have you get a new set of LIDAR data every few years for a given area, and you can see landscape change on human timescales. And you can see the effects of flooding or bluff erosion or coastal erosion or changes in landslides. Another thing that I've worked on a fair amount are a number of landslides that we have up here in the Northwest Washington. And you can actually track the rates of change of those landslides or see the activity of those landslides through repeat LIDAR and measure them in incredible detail. I'm not, I have to admit, I'm more of an end user on this. again, I keep calling on Ralph's name here, but Ralph has been one of the primary proponents from the get-go of LIDAR data and getting collected here in Western Washington, where our trees are so thick we can't see the landscape very well otherwise. And he would probably be the one who would know more if there's any true advances. I mean, there's probably some extent I can imagine they're going to get stronger lasers, faster pulsing, and basically be able to sort of see in a finer resolution. The one problem with stripping away the trees is you do strip away a lot of the information when you strip away the trees and get a bare earth landscape. And so your resolution of what you can see gets degraded some depending on how thick the trees are and the leaves and everything else like that. And I have always wondered if you can come up with, if they're thinking about ways to make the lasers more powerful or somehow be able to see more of the ground through time. They also have lasers that can see a ways into the water, so you can actually get into the submarine a little bit. And that's another exciting possibility. I'm not sure how clear the water's going to be for that. There's usually green lasers, I think. But again, I'm not as familiar with the technology. I'm more of an end user. So if they come up with something better, I'm going to love it for sure. So this is what I used to dream about, this sort of thing when I was doing my PhD well before LIDAR. Going in, I was like, God, if we just get rid of these trees or see through the trees, and we didn't have a way to do it. So now we do. It's pretty awesome.
It's been a real revolution for geology in the last 20 years.
It has been. It's been remarkable.
So Doug, I don't see any other, well, there's one, how does LIDAR affect animals or humans when they obtain the data?
It's a good question. And to be honest, they must have safety protocols on it. Again, I'm not familiar with what they are. I'm pretty sure they have to use bandwidths and or intensities that can't damage eyes if someone happens to look up when a plane flies over. And I think these surveys go so rarely for the most part that it's really unlikely that anyone would get zapped by these things. But I got to think that that's a primary aspect that they look into technologically, that they keep the laser pulse low enough that an incidental single pulse beam that would hit you, because it'd only be one pulse because the plane's flying over you. You'd only get one pulse and that would be it. But at the same time, I've got to think that they have it so that it wouldn't actually damage eyes of both animals and humans. But again, I'll bet Ralph knows that. I just don't.
Okay. So I think we'll wrap it up. If you've got lingering questions or something that you wake up in the middle of the night thinking about, just send Doug an email. You've got his address, where he had his address.
It's pretty. Oh yeah, it's pretty simple. It's just Doug.Clark at www.edu. So
I know you've got a birthday party you got to get to.
Yeah,
so.
I do. Yeah, my little one's going to be, well, she'll probably not even know I'm there because they're watching a movie now. I mentioned to Michael and Rebecca that my kids are, because they're mostly not vaccinated still, my kids get their first shot, but not the second one. So we've still got it outside, despite the fact that it's late November, and they're all sitting, we got them little boxes that they got to design car wheels and stuff on. And they're all sitting in these little boxes in our carport, watching a projected movie as a drive-in movie theater with a bunch of 6-year-olds. So.
Okay. Thanks a lot.
All right. Thanks, guys.
Thanks so much, Doug.
Thanks for the invitation.
Can't
wait to get out and see you guys in person at some point.
Okay. That's it. We'll wrap it up.
All
See
right.
you in 6 weeks or so.
Sounds good. Bye to both.